right, let's get started. So I'm first going to just go through a review of what we've done so far. What's the story so far? Well, the first sort of theme that we've treated is that groups are everywhere. We've defined these things abstractly, but really they're very, very concrete. If you're ever trying to figure out what should be true in general of a group, you have a lot of great examples to look at to test your ideas on. So for instance, one of our first examples was GLN-R. Another example we saw was the symmetric group on n letters. And a third example we saw was the group of integers under addition. So when I just write z, I really mean integers with addition. And another of the themes that we hinted at but haven't treated in detail so far is that these things arise as the structure-preserving bijections of something. So what are the structure-preserving things here? Well, this is the structure-preserving bijections for our n with its linear structure. This is just the set of structure-preserving bijections on a set of n elements with just its set structure, no additional structure. And z, there are a lot of ways of sort of realizing z as the symmetries of something. So another sort of thing that we'll be talking about is symmetries of geometric objects. So this is just a hint of something that I'm not going to treat in detail now, but which will be a recurring theme. If I take the sort of infinite directed graph, where I have just a series of vertices, an infinite number of vertices extending out in both directions, and I just have directed arrows, then the symmetries of this thing, well, all I can do is shift it by a certain amount. Again, we'll treat that in greater detail later. Another theme we've discussed is that given a group, there are a whole bunch of other groups that sort of come out of that group. So making new groups out of old. And you should really think of this as being a very familiar sort of procedure. You've seen this sort of thing in great detail in linear algebra. You've seen subspaces of a given vector space, and that's the sort of thing that we saw with subgroups being part of a group. We saw things like the cyclic subgroup generated by an element. Well, that's sort of like having the vector space generated by a single vector. And there'll be a few other things that we'll see later in the course, like products of spaces corresponding or being analogous to products of groups. And then finally, something that I'll start talking about today. We know that stuff like Hom Rn has a vector space structure on it. Well, likewise, given a group, the set of morphisms between G and itself that are bijective form a group. And so we have a lot of analogies, and whenever you want to think about what's going on here, you can often think back. You can often use a lot of your intuitions from linear algebra. A third theme that we've looked at is that in some cases you can actually classify the subgroups of a given group. So last time we considered the subgroups of Z. Now, the argument we used to show that every subgroup of Z is of the form BZ looked innocuous, but it's actually a very significant argument. Again, it's something that's going to come back to haunt us, so it's a very good idea to familiarize yourself well with that argument. Just recall that basically what we did is we took a subgroup, we said, well, if it's non-zero, then there must be some smallest positive integer in it. And then we showed, using the Euclidean algorithm, that every element of the group must be an integer times that smallest positive integer in the subgroup. So in general, though, it's very, very difficult to study the subgroup structure of a given group, but it's also very, very important. And then another thing that we looked at was particular cyclic subgroups. So I'll just refresh your memory on that. So if I have a group, and I have an element of that group, I can consider the set of all powers of that element, and that forms a subgroup. So here are a couple of examples. If I take in GLNR, the element 1101, then, sorry, GL2R, thank you very much, N is 2. The cyclic subgroup generated by this thing, well, it's not hard to see that the powers of this thing all look like 1, N, 0, 1. This you can prove easily by induction, for instance. People who aren't familiar with mathematical induction, maybe you should see me after class. So this is ranging over all integers. So these are a lot of the sorts of themes we've seen so far. And so when you have infinitely many elements in the cyclic subgroup generated by a given element, you say that that element has infinite order. Of course, quite often, elements will not have infinite order. Quite often, there will be just finitely many distinct powers of something. For instance, if I just take, again, in GL2R, minus the identity matrix, then this thing has order 2. I square it, and I get the identity matrix. Sorry? So the first new theme that we're going to talk about today is that of isomorphism. So let's try a very sort of simple way of starting to understand isomorphisms. So let's consider a couple of different groups. So the first group, let's consider, call it G1. We'll make this plus or minus 1 plus or minus I, viewed as a subgroup of C star, which is notation for the non-zero complex numbers equipped with multiplication as the group operation. So it's just a very simple thing. I mean, this is just the powers of I, square root of negative 1, k running through k, 0 through 3. Another group we'll consider is the cyclic subgroup of S4, symmetric group on 4 letters, generated by something I'll call rho. And, well, here's a way of describing what it does. It sort of cycles the things around. It cycles them. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. In a shorthand, we'll be introducing eventually. This might be written 1, 2, 3, 4. Now, you don't have to worry about that, but it's an easy way of just sort of coding what this permutation is. And it's not hard to see that, for instance, well, rho squared is certainly not either the identity or rho. You can see that because if you evaluate rho composed with itself, well, 1 will go to 2, 2 will go to 3. So rho squared takes 1 to 3. And certainly neither the identity nor rho do that. Likewise, rho cubed is not one of E rho rho squared by the same sort of argument, or just using what we've established already in inverting. I mean, if rho cubed equaled rho squared, then, for instance, rho would equal E, which isn't true. But because these things are just being cycled around, it's not hard to see that 1 will end up back at 1 after composing this permutation with itself 4 times, and likewise for 2, 3, and 4. So this is just the identity. So put another way, the multiplication table for this thing, E rho, rho squared, rho cubed, just looks like E rho, rho squared, rho cubed, then shift this row, rho squared, rho cubed, E, rho squared, rho cubed, E, rho, rho cubed, E, rho, rho squared. And that follows immediately from this. But that's exactly the same thing as the multiplication table for I. So in some sense, these are really the same group. They just have the same multiplication table, but they're relabelings of each other. Is that fairly clear, or does anybody not see that?
I have to admit I don't see it right
Okay, sure. So I has the property that its fourth power is 1. But all of the powers in between that and this fourth power are not any of the previous things. So for instance, I squared is not, it's minus 1. It's not the same thing as 1 or I cubed is minus I. That's not 1 minus 1 or I. And so again, by the same sort of thing, when you multiply the things around, it just sort of circulates them. So call this thing G2. The idea is that G1 and G2 have the same multiplication table. But with a relabeling. So this idea of relabeling multiplication tables gets formalized in algebra under the name isomorphism. So I'll write down a definition now. Isomorphism. An isomorphism is a map between two groups, which is bijective, and such that it preserves the multiplication operation. So f of x times y is f of x times f of y, where, of course, over here, this is the multiplication in G1, and this is the multiplication in G2. So this is the same sort of idea. You're just, f is what's telling you how to relabel the things. And the idea that the multiplication table is preserved is just saying that f of x times y is the same thing as f of x times f of y. So here's another example.
In this case, what's the isomorphism?
So in this case, the isomorphism is given explicitly by sending powers of I, so say I to the kth power. So explicitly, in our case, I send the kth power of I to the kth power of rho. So 1 gets sent to the identity, I gets sent to rho, I squared gets sent to rho squared, I cubed gets sent to rho cubed.
That means f of I to the k is rho to the k.
Yeah, so f of I to the k equals rho to the k. Gives us an isomorphism. And a more general fact, which is a very good exercise, which I believe is included in the exercises for today, which I'll put up on the board at the end of class, is the following. So I'll write it as a fact now, and I'll leave part of the thing unproved, and the exercise will be to fill in the gap. So I'm going to use some words and then I'll explain exactly what I mean by them. So every cyclic group of order n, or every two cyclic groups of order n, are isomorphic. So definitions. A cyclic group is just a group such that there is some element in it which generates the entire group. And isomorphic, well, we say G1 and G2 are isomorphic if there is an isomorphism between them. And we'll see shortly that if there's an isomorphism going one way, there's certainly one going the other way, and this turns out to be a good equivalence relation. But we'll see that later. But how do we see that? Well, in brief, and again, you finish this off in the assignment, in the problem set. If I have G1 and G2, and they're both cyclic of order n, and I have elements x1 and x2 that generate, then the map f from G1 to G2, taking the kth power of x1 to the kth power of x2, you can show is a well-defined bijection. Specifically because x1 and x2 have the same order, and that's what the exercise is about. And the preservation of multiplication property is fairly straightforward. That follows just from the fact that if I have x1 to the n times x2 to the m, so f x1 to the n, x2 to the m, well, that's f x1 to the n plus m, that's x2 to the n plus m, and that's x2 to the n times x2 to the m. So really all there is to check is that this thing is a well-defined bijection. Now, let's talk about something which isn't cyclic. Oh, yeah?
Is there a cyclic group of order n for every n?
It turns out there is one. And it's not hard to construct one inside of Sn by just taking the cycle. So in Sn, so the question is about, is there always a cyclic group of order n? Well, in Sn, the cycle, the permutation, taking 1 to 2, 2 to 3, et cetera, on down, n minus 1 to n, and then n back to 1, it's not hard to show has order n. And so the group generated by that is a cyclic group of order n. Yes, your question?
Can you pause for a second?
Absolutely. Yeah.
In that section of the blackboard, did you write f of x1 to the n times x1 to the n?
Yeah, this is x1. Absolutely. Any other questions? Yeah.
On the SN thing that you were doing right there, that was to show what is that?
So in Sn, there's certainly a permutation that looks like this. This is permutation. And call it sigma sub n. And the question was, is there always a cyclic group of order n? And so it turns out there is, because if I take this permutation in Sn, and I consider the cyclic subgroup of Sn generated by this sigma n, then this thing has order n. All right, is everyone caught up? All right, great. So let's look at a different kind of example. Example. Well, consider the real numbers under addition and the positive real numbers, the strictly positive real numbers, under multiplication. A priori, just looking at these things, you wouldn't necessarily expect that they'd be isomorphic. So, but does anybody see something that witnesses an isomorphism? Yeah. Absolutely. So, or putting it another way, what you can do is take f from, so here's G1, here's G2. F from G1 to G2, define it by f of x is e to the x. Well, we know because of the existence of the logarithm, this is certainly a bijection, has the right image and everything. And also, we know just by basic math that e to the x plus y is e to the x times e to the y. So it preserves the group structure. It preserves the multiplication table. So this is an example of a pair of isomorphic groups that are not finite and are not cyclic. Okay, another example, returning to finite groups, but something which is not cyclic. And this is a very useful group to sort of, a very, very small but useful group to test things out on. It's called the Klein-4 group, and I'll give you two ways of writing it. So the first way I'll write it is as a subset of S4. So two ways to write it. So the first one, call it G1. I have just the identity, E. I'll take something, I guess I'll call tau 1, and I'll define it as follows. It'll take one to 2 and 2 back to 1, and it'll also exchange 3 and 4. Tau 2 I'll take to be something that exchanges 1 and 3 and 2 and 4. So 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. Is that clear? And the final element I'll take is tau 1, tau 2. And just by tracing through these things, so first I look at what tau 2 goes to 1, does to 1, say. So tau 2 takes 1 to 3, and then tau 1 takes 3 to 4. So 1 goes to 4. And if I just keep on computing these things this way, I find that 4 goes back to 1, 2 goes to 3, 3 goes to 2. But it's also easy to verify that if I reverse the order, if I take tau 1, if I apply tau 1 to something and then tau 2 to the result of that, then I get exactly the same thing. So just a sort of linguistic point here. we say that these things commute. Tau 1 and tau 2 commute because tau 1, tau 2 equals tau 2, tau 1. So what is the group structure here? Well, what's tau 1 squared? It's the identity. What's tau 2 squared? What's tau 1, tau 2 squared? Exactly. So the group structure is very, very simple. Each of these things, if we multiply by itself, you get E. Obviously, if you take E by any of these things, you get whatever you multiplied by back. And if I multiply tau 1 by tau 2, I get tau 1, tau 2, or tau 2 by tau 1, I get the same thing. What about if I multiply tau 1 by tau 1, tau 2? Exactly. So if I take any of these things of order 2 and I multiply them by each other, I get the third. So here's another way of writing the group. I could just write it as the set of matrices. So in GL2R, say, I could just write it as the set of matrices, well, identity matrix. Where I just change the entries here to minus ones. So certainly these have the same relevant property. If I multiply any of these things by themselves, I get the identity matrix back. And if I multiply any two of the things which have negative entries, then I get the third of the things that have negative entries. So again, they have the same multiplication table, and there's a nice direct bijection. I can, for instance, have the bijection F take E, so I could define F, and it would take E to the identity tau 1 to this, tau 2 to this, and tau 1, tau 2 to this. Okay, great. Yes?
Why do you need to supply the fourth element of the group? I mean, I just give it the first three, what the fourth after the there?
Absolutely. I could have said the group generated by tau 1, tau 2. But if I want to list all the elements in the group, then I better include tau 1, tau 2. So the question was, do I really need to include tau 1, tau 2 in this list? Well, yes and no. If I wanted to say, just consider the group, the smallest group that contains tau 1 and tau 2, well, I could have just said tau 1, tau 2. But if I want to write out the entire group explicitly, all of the elements, then I need to include tau 1, tau 2, and the identity. So okay, so non-example. So the Klein group. So I say the, and this is a confusion that you often make, or a sort of a shorthand that you often make in algebra, and that is that if you have a couple of groups that are isomorphic, you often talk about them as if they're the same group. So although we have two different ways of concretely realizing the Klein 4 group, because they're isomorphic, we talk about it as if there's just the Klein 4 group. So is the Klein 4 group isomorphic to that cyclic group we started with? Yes, absolutely. Pardon me?
Is there a symbol for the Klein group?
I mean, it's not very steady. The question is there a symbol for the Klein group? Different texts will often have different shorthands for it before there's a more sophisticated notion introduced. But yeah, later on we'll see that there's a sort of simpler way of writing it in terms of things which do have a notation. So just as a preview, it's a product of two cyclic groups of order 2. Yes, Peter. I think Artin might use the notation V for the Klein 4 group. So, but if you look in other texts, I'm not sure that it'll have the same notation. But yeah, Artin might use that notation. But so, are these things isomorphic? No. What's an easy way of seeing that they're not isomorphic? Yeah? Exactly. It has, so an easy way of seeing this is that I has order 4, whereas the Klein group only has elements of maximal order 2. So here are some very, very simple ways of checking whether things are isomorphic. So no, the former doesn't have elements of order 4, whereas this does. Has 2 of them, I and minus I. Okay, so here's some easy ways of first checking whether 2 groups are isomorphic or not. Obviously, these won't work in all cases, but some properties to test whether groups are isomorphic. So the first one I'll list is that they have the same order. If they're finite groups or infinite groups, they'd better have the same cardinality because there's a bijection between them. The second thing they'd better have in common is that if one is abelian, the other had better be abelian, and vice versa. And then the third quick thing that you can easily check in a lot of cases is that G1 and G2 had better have the same number of elements of every order. Yes?
Isn't the cardinality of the group just the number of elements in it?
That's, yeah, cardinality is right. So cardinality is a synonym for number of elements. And there's another term we use, the order of a group. So they're often, as in, yeah, you can use them essentially interchangeably, although the term order has different meanings in other contexts. So order is something that's more specific to the language of groups. But as in any sort of language, yeah, they're often synonyms, and there's a lot of redundancy. Okay, so we mentioned earlier that given any group G, we can construct another group out of it by taking its symmetries. In other words, taking bijections between the group and itself that preserve the structure on a group. What's a name for this that we've come up with so far? Exactly. So last time we saw the term automorphism, but today we use the term isomorphism. So an isomorphism between a group and itself is called an automorphism. So here's another example, or here's another sort of construction. So given G, we can construct the set denoted aut G. So these are called automorphisms, which is just a shorthand for isomorphisms between the group and itself. So this is the set, well, as I said, of isomorphisms from G to G, but in the sort of impressionistic language we were using earlier, this is the symmetries of G, or the structure-preserving maps of G. Structure-preserving. Any questions? Okay, so there's something that we haven't verified that we really ought to verify. So I called this a group. this is a little problematic. I mean, we know certainly that composites of isomorphisms are isomorphisms because certainly the composite will still be a bijection, and if you have, say, f and g isomorphisms, then f of g x, y is f of g of x, g of y, which is f g x, f g y. And the identity is certainly there. We have just the usual identity map from G to itself, and that's certainly an isomorphism. But we're missing something, and that is that inverses are still automorphisms. And that's easy to verify, but it's something you certainly need to verify. And I'll give as an exercise. It's extremely easy, but I'll list it as one of the exercises to prove that this thing is a group. So the thing you need to verify, the last remaining thing to verify, exercise in problem set, show that the inverse of an automorphism is an automorphism. Or more generally, that the inverse of an isomorphism is an isomorphism. This isn't hard to see, but it's worth verifying to make sure that you're comfortable with the language. So it's going to be one of the problems I list amongst the things from Artin. Okay. Let's move along to something a little different. So far we've talked about bijections which preserve the structure of a group, that preserve the multiplication operation. But I'm going to introduce a sort of generalization of this idea, things called homomorphisms. So for instance, the determinant map from, say, GLN R to R star, which, again, per our previous notation, is the non-zero elements of R with multiplication as the group operation. Well, it's certainly a well-defined map, and we know that the determinant of AB is the determinant of A times the determinant of B by basic linear algebra. Is this thing an isomorphism? No. What's an easy way of seeing that it's not an isomorphism? Sorry? Yeah, go ahead. It's not one-to-one, for example. Well, so yeah, I mean, there are a lot of easy ways of seeing that in fact, GLN and R star can't possibly be isomorphic, one of them being, for instance, that this is abelian and this is not. So certainly det is not one-to-one, and in fact, there can't be any isomorphism between GLN-R and R star. But nonetheless, it does preserve the group structure. There can be bijections. In fact, these two have the same cardinality, but you can never show that they have the same group structure. So the question was, could there be bijections? Yes, there certainly can be bijections, but they'll never be isomorphic as groups. Yeah. Okay. So the formalization of this idea, where you have some sort of map and it preserves the group structure, but we don't make any sort of assumption that the thing is bijective, that's this idea of homomorphism. So the formalization, homomorphisms are maps F between groups such that f of x times y is f of x times f of y. And so, can people give me examples of homomorphisms? Well, so we've seen, yes, go ahead.
Every isomorphism.
Exactly. Every isomorphism is a homomorphism. Suppose I have a pair of groups, G1, G2. Is there necessarily a homomorphism between them? Does anybody have any ideas? Yeah, go ahead.
No, because they're not necessarily the same order.
Well, that would be a problem if I were asking, is there always an isomorphism between groups? But homomorphisms, we don't know, preserve things like the order of a group.
How about mapping everything to the identity?
Absolutely. So there's always a trivial homomorphism between any two groups. Trivial homomorphism. So between G1, G2. And that's defined by just taking f of x to the identity element of G2. That certainly preserves the group structure because f of x times y, well, that's automatically E, and that's automatically the same thing as f of x times f of y because both of those are E. So on Wednesday, we talked about S3 as if it were a subset of Sn. Is that a bit problematic? I mean, insofar as something that's a function from the set 1, 2, 3 to itself isn't really a function from the set 1, 2, 3, dot, 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 n to itself. But we thought of the elements in S3 as if they were in Sn for n greater than or equal to 3. Well, so this gives us another example of a homomorphism. Because what we really were doing is we were taking things in S3 and we were giving them just the identity structure on 4 dot 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 n. And the whole point was that because of our sort of intuition about these things, we know that the same group structure that was on S3 is going to be preserved onto whatever the image of this map was. So we had S3 to Sn for n greater or equal to 3. Well, what we did is we took some permutation rho in S3 and we redefined the thing. So rho 1, rho 2, rho 3, according to how they're given. And then rho k be just k for k equals 4 dot 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 n. So this is certainly a new permutation. This is something in Sn. But it's easy to verify that this thing preserves the group structure because all we're really doing is we're just saying leave the thing to be the identity on 4 through n and do the things on 1, 2, 3 as before. This thing is injective. So far, only isomorphisms we've seen, we've only seen injective homomorphisms in the case of isomorphisms. But here's an example of an injective homomorphism which is not an isomorphism. Are there any questions? Okay, great. Here's another example. I'm going to take the map F from the integers to the symmetric group on 2 letters, and I'm going to define it as follows. I'm going to take all the even numbers to the identity element, and I'm going to take all of the odd numbers to the transposition in S2 that we introduced on Wednesday or Monday. And it's pretty easy to see that this preserves the group structure because if I add evens to evens, then I get evens. If I add odds to odds, I get odds. And if I add evens to odds or odds to evens, then I get odds. So this thing is certainly a homomorphism. It's well defined. And it's another sort of example of a homomorphism. And it's going to be a sort of nice replicated example. We're going to see this sort of thing again and again. Okay. Another piece of terminology. Images. So the notion of image is about seeing a group through the lens of a homomorphism. So suppose I have f going from G1 to G2. So I'll just draw these things as some sort of blobs. Not everything in G2 is necessarily going to be hit by f, but some subset of it will be, certainly. So here's G1, here's G2. And the shaded in part, the part that's hit by G1, is called the image. Now, this is a familiar notion. This is from linear algebra. There were a couple of different names. You might have called it image. You probably also called it column space of a matrix. In our case, we just call it the image, and it's the set of f of x in G2 as x ranges over G1. And the main professor, Professor Gross, will pick up on this next time. Are there any questions about what we've done so far? All right, great. Now I'm going to list the homework exercises. It's actually it's on the problem set. It'll be posted online as well, but. So a couple of these you've seen already in more or less detail in class today, but it's still a very good idea to work through the details of it. All right, great. This is due on Monday. So Friday assignments are due on Mondays, etc. Yeah, go ahead. Yeah, there will be solutions posted to the assignments. Okay, great. Yeah. All right, so the way this is going to work, at least for the beginning, for the first while, is that you won't necessarily get your homework back on the next lecture after you handed it in, but in general, you'll be getting your homework assignments, accumulated homework assignments back on Wednesdays.